So now we're going to start our next section, which is 12.5, and it's about arc length and curvature. So we're going to start with arc length, and let me define arc length here. So if C is a smooth curve given by R of t, which will be x of ti plus y of tj plus z of t k on an interval a to b, then the arc length of C on the interval is S, is what we're going to use for the arc length, S. It's the integral from a to b of the square root of x prime of t squared plus y prime of t squared plus z prime of t squared dt. And if you look, this kind of reminds you of a magnitude because there's a square root. So this is the magnitude of the vector r prime. So there's our formula right here for arc length. I'll box it in so that we have it saved. So there's how we compute arc length. And let's look at an example problem where we need to compute arc length. So for example, let's find the length of one turn of the helix given by R of t. It's going to be b cosine ti plus b sine tj plus the square root of 1 minus b squared tk, where t is going to be between 0 and 2 pi. It's going to give us one turn of the helix. So if I want to find arc length, I need the derivative of r. So we're going to find r prime of t. It's going to be negative b sine ti plus b cosine tj plus the square root of 1 minus b squared k. And so now we're going to find arc length, plug it into our formula, S. It's the integral from 0 to 2 pi, and then it's the magnitude of the derivative, r prime. So it's the integral from 0 to 2 pi. So when I compute this magnitude, you're going to get b squared plus 1 minus b squared. And that just simplifies down to 1, the square root of 1, which is just 1. So when I integrate 1, I'm going to get t back from 0 to 2 pi. So you're going to get 2 pi for the arc length of this one turn of the helix.